So we've talked about intermolecular forces, IMFs, and we've specifically talked about one type of intermolecular forces, which are hydrogen bonds, H bonds. In this video, we're going to discuss another type of intermolecular force, which are called dipole-dipole forces, okay? Sometimes referred to as dip-dips. So what we want to be able to do with dipole-dipole forces is the same thing we've done with other intermolecular forces, is look at a molecule and be able to determine whether or not it will have dipole-dipole forces, dipole-dipole interactions, and then use that knowledge to explain phenomena of boiling points, melting points, etc. So what we first need to know about dipole-dipole forces, okay? First, we've learned this term dipole before. We learned that, for example, in the molecule, or let's draw a bond between oxygen and hydrogen. We know that since oxygen is more electronegative than hydrogen, it's going to have a slight negative charge, and hydrogen will have a slight positive charge. As a result, we learned that this was a polar bond. We also learned that a way to describe this is that it has a dipole. So when we're talking about dipole-dipole forces, dipole-dipole intermolecular forces, these occur in polar molecules, only in polar molecules. Another way of saying that is they only occur in molecules that have dipoles. And the reason for that is what we described over here, because dipoles create a positive side and a negative side of a molecule, and we know that opposite charges tend to attract each other, which is a type of intermolecular force. Other thing we need to know is that dipole-dipole forces are permanent. Okay? They always exist. If a molecule is polar, if it has a dipole, it will always have dipole-dipole intermolecular forces. A third thing that we need to know that these are weaker than hydrogen bonds. So now we're going to start discussing the strengths, the relative strengths of all these forces. We've learned about hydrogen bonds. They have the biggest effect on boiling points, melting points, etc. They're the strongest type of intermolecular forces. After hydrogen bonds come dipole-dipole. They're weaker than hydrogen bonds in their strength. So, for example, let's look at some molecules. Our good old friend methane, CH4. Let's discuss, does this have dipole-dipole forces? Well, now we're using all of our knowledge of Lewis structures, polarity, electronegativity, molecular geometry to answer this type of question. So if we drew the Lewis structure, hopefully you can do this kind of by memory by now. This is what CH4 looks like. First thing that we would remind ourselves of is that it's tetrahedral shape. It has a bond angle of 109.5 degrees, just some side notes from molecular geometry. And we learned that we're going to have dipoles pointing in all these directions. And all these dipoles are going to cancel out. So therefore, CH4 is nonpolar. So since it's nonpolar, this cannot have dipole-dipole forces. Dipole-dipole IMFs, intermolecular forces. Okay? We also know it can't have hydrogen bonding because carbon is not a FON, F-O-R-N. So this can't have hydrogen bonding or dipole-dipole forces. So that kind of helps to explain the boiling point of methane, which is in the negative something degrees Celsius, negative 70 degrees Celsius or something like that. But let's talk about another molecule. What about hydrochloric acid, HCl? Okay. HCl, if we drew the Lewis structure for it, would look like so. Oh, that's a little fat H. Okay. Here's the Lewis structure for HCl. So we got to think, is this polar? If we're trying to determine if it has dipole-dipole forces, first question you have to ask yourself, is it polar? Well, chlorine we know is more electronegative than hydrogen, so it's going to have a slight negative charge. So yes, this is a polar molecule with a slightly negative charge towards chlorine. So therefore, by definition, if it is polar, it has dipole-dipole forces. Dipole-dipole intermolecular forces. So what would that look like? How would we draw, like, let's say, 4 HCl molecules next to each other with their intermolecular forces? So let's say we drew, here's one HCl. So now we know that this chlorine is going to have the slight negative charge. The hydrogen is going to have the slight positive. So the intermolecular force, this chlorine is going to have to be near a hydrogen on another molecule. And then this chlorine could be near another hydrogen. And then this one could be near another hydrogen. Again, the reason for this, because chlorine is slightly negative, so it's going to be next to this positive charge here. And that works for all of these examples. So this would be a representation of the dipole-dipole intermolecular forces seen in HCl. Again, what I'm circling in green here, those are the intermolecular forces because they are between 2 different molecules. For example, between this molecule and this molecule, this one, and this one. How can we use that knowledge to explain some trends in boiling point? Well, here's an example. The boiling point of ethane, C2H6, is 184 Kelvin. The boiling point of fluoromethane, CH3F, is 195 Kelvin. Explain these differences. So, whenever we're doing this, we need to think about, with intermolecular forces, we want to know the structure. So, Lewis structure for C2H6 would look like so. And the Lewis structure for fluoromethane would be CH3 with the fluorine on one side. Again, the fluorine, it doesn't matter where it is, it's just on one side of the carbon. So we got to ask ourselves, polar or not? Well, this molecule is symmetrical, and all the atoms are equivalent. So these dipoles cancel, same up here, these all cancel, these cancel, and this bond here has no dipole because they're the same atom, so they have the same electronegativity. So this is non-polar. So it has no dipole-dipole, dip-dips. What about the other molecule? Here we have this dipole cancels with this one, and over here we are going to have an uneven balance of charge, uneven distribution. So this fluorine is going to be slightly negative compared to this carbon. So yes, this molecule is polar. So since it's polar, it's going to have a dipole-dipole intermolecular force. So how does that explain the boiling point? This is 195 Kelvin, this is 184. So one way we could explain this molecule has a higher boiling point because it has more intermolecular forces. It has dipole-dipole forces, whereas the other molecule doesn't. So that could account for the need of a higher temperature in order to boil this molecule, convert it from a liquid to a gas. Neither of them have hydrogen bonding, so that's not going to play a role. The only thing that's different are these dipole-dipole forces. We'll learn about other forces called London dispersion forces in a different video, but for now, to determine if a molecule has dipole-dipole forces, you need to ask, is it polar? If it is, it has dipole-dipole interactions. One last thing as a visual, this is always good practice. What would this molecule look like if 2 of them were exhibiting this distribution? We know the fluorine is slightly negative, so it's going to want to be next to the slightly positive hydrogen on the other side. So this could be one example of how we drew the the interaction here. This would be the dipole-dipole intermolecular force that's between these 2 molecules.